is a very important set, and its properties, which we have actually proved in these preceding lemmas, will now be consolidated, taken together, and we will state a theorem, and that theorem will be very important for us. So let us now state the theorem with the help of these lemmas. The theorem will need actually it needs a proof, but its proof will involve repeating those lemmas that we have seen just now. So let us mention the theorem. If sigma, tau and mu are elements of A of S, keep in mind that we have defined A of S only when S is a non-empty set. So S can be any set, but it has to be non-empty. So that means whenever we are writing A of S, it is assumed that S is non-empty. So we are not saying here anything about S, but it is presumed that S is non-empty. Okay, then there are four statements which are true. The first one is that this is again an element in A of S. The second one is the associative law. Note that in the general associative law we had different sets, right, where sigma was from S to T, tau was from T to U, and mu was from U to V. Okay. Here, however, all the sets are S. So there is no problem in forming these compositions at all. You don't even have to think about whether these compositions can be formed. In fact, you can take one more function or mapping, and you can take composition of that with this one. Okay, because ultimately all of them will map S to itself. So you can repeat it as many times as you want. The third one, there exists an element iota belonging to A of S, which is actually nothing but the identity map on S. And the identity map. Map, we write in short map, actually it is mapping, such that sigma composition iota is equal to sigma. This is equal to iota composition sigma. Iota does not have any effect on this sigma or on the composition. Okay, we start with some element, we get that element back. And number 4, we have not mentioned about inverse. Okay, I will say it. There exists an element. So that means I have to say it slightly differently. an element mu we have already taken. Let me call it sigma star in A of S such that sigma composition sigma star is equal to iota, which is equal to sigma star composition sigma. Okay, so these are the four properties which are going to be very important in the next chapter, which is on group theory. So these things are true in A of S, and those of you who already know about group theory, they know very well that A of S forms a group under the operation which is composition of maps. Okay, now having stated this theorem, since I have had to use a weird symbol for the inverse of sigma, let me just set things straight. You can probably understand that actually this sigma star is nothing but the mapping mu in the third lemma. Associated to sigma we have a mapping mu such that if sigma composition mu is the identity on S and mu composition sigma is the identity on T. But here, since we have only one set S, so we have just one identity, which is the iota. Okay, in the above theorem, sigma star is called the inverse mapping of sigma. In brackets we write it is nothing but the mapping mu in the proof of lemma 3. It is that particular map, inverse mapping of sigma, and is denoted by the symbol, sigma inverse. One question may arise at this point that what is the guarantee that this inverse is unique? Because the way we have stated the third lemma, it just says that there exists for sigma, there exists a function mu such that sigma composition mu and mu composition sigma are identity maps on their respective sets. It does not say anything about whether there may be more than one mu. But actually it can be proved with the help of these properties itself that the mu or the sigma inverse that we get is unique, and that's why we can use a symbol which is associated with sigma. It is justified. And lastly, there is a lemma, fourth lemma, which gives some insight into the behavior of this composition as an operation. We have already seen this in the examples, but we are now going to see it somewhat more generally. The fact that composition, although it is associative, it's not commutative. It's not always commutative. In most of the cases, it's not commutative. And the precise statement is this: if S has S is a set has more than two elements, then we can find elements sigma and tau in A of S such that sigma composition tau is not equal to tau composition sigma. And the proof is not very difficult. In fact, part of the proof we have already done in the examples of that we have seen, those examples 11, 12 and 13. There itself the parts of the proof are there. Okay. Note that it is given that S has more than two elements, so that means we can find three distinct elements in S. Let x1, x2 and x3 be three distinct elements in S. Okay, define. We are now going to define the mappings sigma and tau. That will give us that non-commutativity. So define sigma from S to S by x1 sigma equal to x2, x2 sigma equal to x3, x3 sigma equal to x1, and x sigma is equal to x for all x belonging to S minus x1, x2, x3. Okay, if S has more elements, then they are not changed by sigma, and x1 is mapped onto x2, x2 onto x3 and x3 onto x1 by sigma. So that is the definition of sigma. And we define tau from S to S by x1. Okay, we can write it like this: x2 tau is equal to x3, x3 tau is equal to x2, and x tau is equal to x for all x belonging to S minus x2 comma x3. Note that this means that tau maps x2 onto x3, x3 onto x2, but maps everything else onto itself. That means tau maps x1 onto x1, which sigma does not do. It maps x1 onto x2. Okay. Now let us calculate x1, the image of x1 under sigma composition tau. x1 sigma tau, we have already calculated this type of things. So x1 sigma is x2 and this is equal to x3, whereas x1 of tau composition sigma is x1 tau sigma. Now x1 is unchanged by tau, so x1 stays x1, x1 sigma is x2. So the images of x1 under these two maps are different, x2 and x3. So the maps cannot be equal, hence sigma composition tau is not equal to tau composition sigma, and this proves the lemma 1 to 4. In the language of group theory, if I say prematurely, I am saying it just says that these groups are non-abelian or non-commutative if S has more than 2 elements, that is 3 or more elements, and the smallest such group you already know is denoted by S3, the symmetry group of degree 3. Okay, so we will see about these things in the coming videos, but